Assalamualaikum warahmatullahi wabarakatuh and a very good day to everyone. Today we will learn chapter 2-2 which is on optical detectors. Okay, as an introduction, the detector is an essential component of an optical fiber communication system. Okay, so let me refresh back the basic component of optical fiber communication system. So usually you will have the transmitter, okay, at the beginning of your optical fiber communication system. So your transmitter can be either a laser or an LED. And then you will have your fiber, okay, either a single mode fiber or a multi-mode fiber. And then you will have your receiver. Okay, so this receiver is actually your detector. Okay, so the received optical signal is generally weakened and distorted. So of course our received signal is weak and distorted, okay, because of the attenuation and the dispersion effect. Okay, so thus photodetector must meet a very high requirement and high performance requirement. Okay, so the function of this receiver or the detector is actually to convert the received optical signal into an electrical signal, and then it will be amplified for further processing. Okay, there are two distinct photo detection mechanisms. The first one is external photoelectric effect, and the other one is internal photoelectric effect. Okay, for external photoelectric effect, the electrons are freed from surface of a metal by the energy absorbed from an incident stream of photons. Okay, so usually we have metal, okay, whereas the electrons are freed from this metal by the energy that is being absorbed, okay, which is in the form of photons. Okay, so that is for external photoelectric effect. Example of application is on the vacuum photodiode and photomultiplier tube. Okay, so for internal photoelectric effect, the semiconductor junction device which free charge carriers, okay, the free charge carriers is either electron and holes, are generated by the absorption of incoming photons. Okay, so you can see here, for example, this is the incoming photon. Okay, our light, our incoming photon, and it is being absorbed by this semiconductor device. Okay, and then after a certain threshold value, okay, the free charge carriers, which is the electron and holes, are generated. Okay, and then it will be flowing. Okay, it will flow in this circuit. Okay, so that current will flow. Okay, so the positive charge will be attracted to the negative terminal of this battery, and the negative charge will be attracted to this positive terminal of the battery. Okay, so that's why when you connecting the PN junction, okay, the PN junction device, you need to reverse biased. Okay. Okay, so before you proceed with my next slide, please look into these two YouTube links to know more on diode and also on photodiode. Okay, so these are examples of diode and photodiodes. Okay, so now let us look on photodiode pin structure. Okay, pin photodiode structure. Okay, so you can see we have the P type and also the N type, and in between here you have the intrinsic region. Okay, so that's why we call it as pin photodiode. Okay, so this is the figure or the pin photodiode structure when it is not connected to the battery. Okay, so for P type, of course, the majority carriers is the holes. Okay, and for N type, the majority carriers are the electron. Okay, so no carriers in the I region. So you can see here, inside here, there is no carrier. Okay, we still have the depletion region, but there is no carrier inside here. And of course, there will be no current flow. Okay, so this is the structure of the pin photodiode. Okay, it is connected to this battery. Okay, so you have it is connected in reversed bias position. You can see p-type is connected to the negative terminal, n-type is connected to the positive terminal. So that is why it is reversed bias. Okay, so assuming there is a load resistor here. Okay, so when the incoming photon arrived at the depletion region, so basically photons will generate the electron hole pair. Okay, so electron hole pair will be generated in the intrinsic region. Okay, so our depletion region will become wider. Okay, so when it reach a certain threshold value, then it will have enough energy so that this free electron hole pair can move towards the battery terminal. Okay, so of course for this negative terminal, the holes will be attracted, and for the positive terminal, the electron, okay, so you can see the free electron here will be moving towards this positive terminal. Okay, so the whole process will generate a current flow. Okay, so the current flow through the diode. Okay, so that is how generally the pin photodiode is functioning. So again, this is an optical detection principles. So at first, the absorption of photon in the photodiode, and then it will produce carrier pairs, the electron hole pairs, and thus a photocurrent or the current IP will be produced. Okay, the absorption is dependent on the absorption coefficient. So of course, absorption depends on the absorption coefficient alpha naught, which is the absorption coefficient of the light in the semiconductor used to fabricate the device. Okay, so different device or different photodiode will have different absorption coefficient alpha naught. So alpha naught is strongly dependent on the wavelength. Okay, light falling on a photodiode is partially absorbed and partially transmitted. Okay, so only the absorbed photon will be converted into photocurrent. Okay, so the transmitted photon is actually a loss to us. Okay, so the Px, which is the power absorbed, is equal to power incident times with 1 minus exponential negative alpha naught d. Okay, alpha naught is our absorption coefficient and d is the width of absorption region. Okay, so you can see from this equation when alpha naught goes to 0, okay, so alpha naught equal to 0, exponent 0 is 1. Okay, so 1 minus 1 is 0, so the power absorbed is equal to 0. Okay, so when alpha naught goes to 0, the absorption power is also equal to 0. When alpha naught goes to infinity, the power incident is equal to the absorption power. Okay, so it means that it is a good absorption device. Okay, so this is the absorption coefficient for different material. Okay, so you have the gallium arsenide photodiode, the silicon photodiode, okay, the germanium photodiode, and these are other materials. Okay, so this is the absorption coefficient alpha naught versus the wavelength. So you can see that the absorption coefficient really depends on the wavelength. Okay, so depending on your application, you should be able to determine what type of suitable material to use as your photodiode. Okay, for a given semiconductor material, the photodiode can detect only certain wavelength. So we know that the photodiode can only detect certain wavelength. So basically, the photodiode will stop to operate above lambda c. Okay, so usually the photodiode will operate lambda c and below. Okay, so lambda c is equal to hc over eg. Oh, EG or WG. So EG is actually the band gap energy. So EG, the unit is in electron volt. Okay, so you know that Hc, okay, the Planck constant time with the light velocity. Okay, so when you multiply both of these, you will get the value is actually 1.24, but for lambda c, the unit must be micrometer. Okay, and this EG depends on the type of your material, which is the band gap energy. Okay, so for wavelength longer than lambda c. Okay, so if it is more than lambda c, then the photon will travel through the material without interaction, which is a loss, because no absorption occurs. So if there is no absorption, it means that there is no photocurrent. Okay. Okay, there are 4 important detector properties that you will learn. Okay, the first one is detector responsivity, or R. Okay, so R is detector responsivity. Okay, it is actually the ratio of output current, okay, this one, the output current to the input optical power. Okay, so hence this is actually the efficiency of the device. Okay, so responsivity, okay, so you can see either, you can use this symbol or R as the responsivity value. Okay, so R is equal to IP over P naught. Okay, IP is the photocurrent. Okay, the unit is ampere because it's a current. Okay, P naught is the incident optical power and the unit is watt. Okay, so units are the units for responsivity. Of course, it is ampere per watt. Okay, so responsivity is a useful parameter as it gives the transfer characteristic of the detector. Okay, the relationship for responsivity may be developed to include quantum efficiency. Okay, so now you have the formula for quantum efficiency. Okay, so this is the symbol for quantum efficiency. Number of electrons collected divided by number of incident photons. Okay, Re over Rp. Re is number of electrons collected. Rp is number of incident photons. Okay, so that is quantum efficiency. Okay, so we can rewrite, or if we want to know the value of number of electrons collected, Re, the formula is actually Re equal to efficiency times with P naught divided by HF. Okay, P naught is the power, the optical power. H, the Planck constant. F is the frequency. Okay, so if I want to write in terms of photocurrent, okay, the output photocurrent, IP is equal to quantum efficiency times with the optical power P naught times with the electron value divided by HF. Okay, and we can also rewrite the final expression for responsivity R, which is equal to IP over P naught. Okay, IP over P naught. So this responsivity is equal to efficiency times E divided by HF. Okay, so again, HF is equal to HC over lambda. Okay, so that's how you get this final formula. Okay, so this is the photodiode responsivity. Okay, so you can see this is for responsivity versus the wavelength. Okay, so different wavelength will have different responsivity, okay, for different material. So you can see this is for silicon photodiode. That is how the responsivity and the wavelength. Okay, this is for germanium and this is for indium gallium arsenide. Okay, so you can see indium gallium arsenide has the highest responsivity, which is the best one. Okay, of course, because the higher the responsivity, the better the performance. And also it covers a wider wavelength. Okay, a large wavelength content. Okay, so silicon is the least expensive. Okay, it has the advantage for silicon, whereas it is the least expensive. Okay, germanium is the classic detector. Okay, and for indium gallium arsenide, okay, so it has the highest speed. So that's why for current technology, usually they use indium gallium arsenide as the material for the photodiode. Okay, the other properties for photodiode is spectral response range. Okay, so this is actually the range of wavelength over which the device will operate. Okay, spectral response range. Okay, it refers to the curve of detector responsivity as a function of wavelength. Okay, so because of the rapid change in responsivity with wavelength, different detector must be used in different region of optic spectrum where losses are low. Okay, so the other properties that we should look into in determining the photodiode is the response time. Okay, so response time is actually the measure of how quickly the detector can respond to the variation in the input light intensity. Okay, so of course, the lower the response time, the better the photodiode is. Okay, because it means that the photodiode can detect very quickly to the variation of light. Okay, you should also look into the noise characteristic. Okay, the level of noise produced by the photodiode. Okay, it is critical to its operation at low level of input power. Okay, so you should also look at the level of noise produced by the photodiode, especially it is very critical when it is operation at a low level of input light. Okay. Okay, try to do this exercise. Okay, the answer I have already put it in the Google Classroom. Okay, let us see on semiconductor photodiode. Okay, semiconductor junction photodiode are small, light, sensitive, fast, and they can operate with just a few bias voltage. Okay, so basically these are the advantages of using semiconductor photodiode. Okay, so in semiconductor photodiode, there are two categories. The first one is without internal gain, and the other one is with internal gain. Okay, the photodiode without internal gain is either PN photodiode or an PIN photodiode. Okay, the photodiode with internal gain is the APD, avalanche photodiode. Uh, Avalanche photodiode. Okay, so that is the photodiode with internal gain. Okay, so for the photodiode without internal gain, it will generate single electron hole pair per absorbed photon. Okay, so every absorbed photon will only generate a single electron hole pair. Okay, but for semiconductor photodiode with internal gain, at the depletion region, while most of the photons are absorbed and the primary carrier pairs are generated, there is a high field region in which holes and electrons can acquire sufficient energy to excite new electron hole pairs. Okay, so more electron hole pairs are generated. Okay, because it has internal gain. Okay, so there are three, as I've mentioned before, there are three forms of photodiodes: PN photodiode, PIN photodiode, and the last one is the most advanced one, which is APD. Okay, so usually, of course, this APD is more expensive as compared to the PIN and also PN photodiode. Okay, so now let us look on PN photodiode. Okay, so basically the principle of PN photodiode is the same as LED but in reverse. Okay, so you can see here, at first, this is our PN photodiode. It is connected to the battery. Okay, so it must be connected in reversed bias position. Positive connected to the N-type. Negative terminal will be connected to the P-type. Okay, so at first, we still have the depletion region, but just a thin depletion region. Okay. So light is absorbed at the PN junction rather than emitted. So basically, at this junction, the light will be absorbed. Okay, at this depletion region. Okay, a reverse bias PN junction passes no current unless something happens to promote electron from the valence band into the conduction band within the depletion zone. Okay, so when there is no light, okay, when there is no incoming photon, okay, there will be no current flow. Okay, but at ordinary room temperature, there is still a small current of this due to the action of heat, and thus a very small current is produced. Okay, but even though it is at room temperature, still we have heat at this PN photodiode. So some of this electron and hole will be flowing in this circuit. Okay, so that's why we still have a very small current. Okay. Okay. When there is incoming light or incoming photon, okay, so this depletion region will become wider. Okay, so it will become wider, and when it reach the threshold value, you will find that the electron hole pairs, you will have more electron hole pairs, and it will have enough energy to come out from this PN photodiode. Okay, so this hole will be attracted to the negative terminal. Okay, so the hole will flow in this circuit. Okay, and this electron will be attracted to the positive terminal. Okay, so this electron will flow through this circuit. Okay, so the whole process will produce the photocurrent. Okay, now let us look on PIN photodiode. Okay, the answer to the problem for PN photodiode, whereas it has a thin PN junction. Okay, so PIN photodiode is actually the solution for the thinness of PN junction. Okay, so as compared to PN photodiode, a PIN photodiode has a thicker depletion region. Okay, so this is an advancement because it has thicker depletion region. Okay, which allows a more efficient collection of carriers and thus a large quantum efficiency and leads to a lower capacitance and thus a higher detection bandwidth. Okay, so PIN photodiode has thicker depletion region as compared to PN photodiode. Okay, the junction is extended by the addition of very lightly doped layer called the intrinsic zone between the P and N doped zone. Thus, the device is called PIN photodiode rather than PN photodiode. Okay, because we have the intrinsic region. Okay, so this is the PIN structure. Okay, so you can see this is the P type, this is the N type, and this is the intrinsic region, the very lightly N doped. Okay, so this is our incoming photon. Okay, so of course, if it has a thicker region, of course, it will produce more electron hole pairs. Okay, and more photocurrent will be produced. Yes, so the white intrinsic layer has only a very small amount of dopant, and it acts as a very wide depletion region. Okay, so as I've mentioned before, it has thicker or wider depletion region for PIN photodiode. There are a number of improvements here. It increases the chances of photon absorption because the volume of absorbent material is increased. Okay, so more photon will be absorbed. Because it makes the junction wider, it reduces the capacitance across the junction. The lower the capacitance of the junction, the faster the device response. And finally, it increases the width of the depletion layer. favors current carriage by the drift process, which is faster than the diffusion process. Okay, now let's look on APD photodiode. Okay, the avalanche photodiode. Okay, it is a semiconductor junction detector that has internal gain, which increases its responsivity as compared to PN and PIN photodiode. Okay, the gain are available make APD much more sensitive as compared to PIN or PN photodiode. Okay, so if you look at the sensitivity of this APD, of course, it is higher because APD is much more advanced. Okay, it has higher sensitivity. Okay, so this internal gain yields much better signal to noise ratio that can be obtained with external amplification. APD amplify the signal during the detection process. They use a similar principle to that of multiplier tubes used in nuclear radiation detection. Okay, so let's look at the physical principle of PIN photodiode. Okay, so this is a PIN photodiode. So you have the intrinsic region. They are in reverse bias position. Okay, the PIN is connected to the bias voltage. Okay, you can see it is reverse bias, negative connected to the p-type, positive terminal connected to the n-type. Okay, so at first photon is transmitted to this intrinsic region. Okay, there is an incoming photon here. It will create the electron hole pairs. Okay, so when the radiation is greater than the band gap energy of the material, okay, for example, 1.12 electron volt for silicon. Okay, for silicon, it will excite the valence band electron into the conduction band. Okay, so when the electron is excited from the valence band to the conduction band, it will cause a current or photocurrent to flow in the external circuit. Okay, so that's how actually the production of photocurrent. Okay. Okay, now let us look on the structure of APD. Okay, basically you have the additional region, which is the pi region and also the p region. Okay, so the pi region is actually where the incoming photon will arrive. Okay, so it is more wider than the intrinsic region in PIN photodiode. Okay, the pi region here. Okay, so that's why it can absorb more photons. Okay, and then at the P region is where the amplification process will occur. Okay, so you can see this is the P region. This is where the amplification will occur. Okay, this one, the figure for P region has been enlarged. Okay, to show the avalanche process. Okay, so you can see this is the pi region, this is the P region, this is the P type, this is the N type. Okay, so this is the structure for the APD photodiode. Okay, so let's look on the explanation. The main structural difference between APD and PIN is that in PIN, we have the I zone, the intrinsic zone, which is lightly n-doped. Okay, for PIN, it has intrinsic zone, which is n-doped. But for APD, it has a lightly p-doped, and we rename it as pi layer. Okay, it is typically thicker than the I zone. Okay, the pi layer is thicker than the I zone, and the device is carefully designed to ensure a uniform electric field across the whole layer. The guard ring serves to prevent unwanted interaction around the edges of the multiplication region. Okay, the multiplication factor M is a measure of internal gain provided by the APD. Okay, so M, the multiplication factor, only occurs for APD. Okay, so the formula for M is I, the total current at the operating voltage, divided by IP, the initial primary photocurrent. Okay, total output current divided by initial primary photocurrent IP. Okay, so that is the multiplication factor. Okay, the formula for M. Okay, so the current generated by an APD with gain M is given by this formula. I equal to M times efficiency. Okay, so this is the efficiency. E, the electron value. P naught, the optical power, divided by HF. H, Planck constant. F, the frequency. Okay, so you know that HF equal to HC over lambda. So that's how you get this formula. Okay, so we can also rewrite the responsivity. Okay, the responsivity for APD, which is equal to responsivity equal to M, the multiplication factor, times with the efficiency times E divided by HF. Okay, so if you notice, the formula is the same as PN photodiode. Okay, the current, the responsivity, except that we have M, additional M here. Okay, this one also we have M because of the multiplication factor. Okay, for the bandwidth, the ultimate bandwidth is limited by the drift time of the carrier through the depletion region. Okay, so the bit rate or the bandwidth is limited by the carriers through the depletion region. When assuming no carriers are generated outside the depletion region and the junction capacitance is negligible, the maximum photodiode 3 dB bandwidth is given by this formula. Okay, so the bandwidth for the photodiode is 1 over 2 pi drift time. Okay, so this is an example of a data sheet for a photodiode. Okay, so this is silicon, germanium, and indium gallium arsenide. Okay, so for silicon, we can have either a pin or an APD. Okay, germanium also we can also have for pin and APD, and same goes to indium gallium arsenide. And you can see that the operation wavelength are much more wider for indium gallium arsenide. Okay, so you can also see for pin and APD, the responsivity is of course bigger for APD as compared to pin photodiode. Okay, so you can see between APD and pin, APD of course has higher responsivity as compared to pin. Okay, so in terms of quantum efficiency, okay, so you can see also the difference between the quantum efficiency. But for bias voltage, we will need higher bias voltage for APD as compared to pin. Okay, the same goes to this and this type of photodiode, germanium and indium gallium arsenide. Okay, the dark current produced is different. Okay, produced in the pin and APD, and these are the rise time value and also the capacitance value. Okay, now let us look on noise. Okay, noise. The definition of noise is actually any spurious or undesired disturbance that masks the received signal in a communication system. Okay, any undesired disturbance that masks the received signal. That is actually the noise. Okay, so there are three main types of noise: the thermal noise, short noise, and also dark current noise. Okay, so we will see further in the next slide. Okay, let's look on the first noise, which is thermal noise. Okay, another name for thermal noise is Johnson noise or Nyquist noise. Okay, so thermal noise is actually a spontaneous fluctuation due to the thermal interaction. Example, between free electrons and the vibrating ions in a conducting medium. Okay, thermal noise current is produced by a current source generating the mean square current. Okay, so this is actually the mean square thermal noise current. Okay, so this current is mean square current is equal to 4 kT delta F divided by RL. K is the Boltzmann constant, the value is fixed. T is the temperature in Kelvin. Delta F, the receiver's electrical bandwidth. Okay, delta F is one word, or you can also replace it with BW. Okay, and RL is the resistor in the optical receiver. Okay, so the unit must be ampere squared because this is the mean square current. Okay, if you are asked what is the thermal noise current. Okay, this is thermal noise current but squared, right? So if you are asked what is the thermal noise current, you need to square root this value. Okay, so that you can get the value in ampere. Okay, so for this formula, the unit is ampere squared. Okay, so let's see the next noise, which is short noise. Okay, short noise is the discrete nature of electrons which cause a signal disturbance. Okay, so in photo detector, incoming optical signal generate discrete charge carriers which contribute a single pulse to the total current. Okay, so short noise results from the fact that the current is not a continuous flow, but the sum of discrete pulses in time, each corresponding to the transfer of an electron through the conductor. Okay, so that is short noise. Short noise can be represented consisting of a single current source. The mean square short noise current is given by this formula. Okay, so again, this is the mean square short noise current. Okay, it's mean squared, so the unit will be ampere squared. Okay, so if you just want to find the short noise current, you need to square root this value. Okay, so you can see the formula is I squared for short noise current equal to 2E IP, the photocurrent value, delta F, the receiver's bandwidth. Okay, E, the magnitude of electron charge. Okay, so short noise increases with an increase in the incident optical power. Okay, so because short noise is proportional with IP, right? So when IP increase, short noise will also increase. Okay, when the photocurrent increase, short noise will also increase. This differ with thermal noise, which is independent of the optical power level. So of course, for thermal noise, it does not depend on IP. So it is independent with the optical power level. Okay, now let us see on dark current noise, ID. When there is no optical power incident on the photo detector, a small reverse leakage current will still flow from the device terminal. Okay, so when there is no optical power incident, actually we will still have a small reverse leakage current on the detector. Okay, and we call it as dark current noise. Okay, so the dark current noise will contribute to the total system noise and gives random fluctuation. Okay, so the mean squared dark current is given by this formula, 2E ID times with delta F. E, the magnitude of the electron, ID, the dark current, okay, and delta F is the bandwidth of the receiver. Okay, so it may be reduced by carefully design and fabrication of the detector. Okay, the mean square of the total short noise current is given by this formula. Okay, so this is the total short noise. Okay, so if you can see from this formula, it is actually dark current noise plus with the short noise. So this is the total short noise. Okay, the mean square of total short noise. Okay, again, the unit is ampere squared. Okay, the unit for this is also ampere squared. Okay, so if you just want to find the dark current, you need to square root this value. Okay, so now let us look on the signal to noise ratio, SNR. It is a measure to quantify how much a signal has been corrupted by noise. Okay, basically, the higher the SNR, the better the signal is. Okay, so SNR equal to power signal divided by power of noise. Okay, so usually the unit is in decibel. Okay, but for decibel, you need to log the value. Log the obtained value. Okay. It will compute the SNR considering with internal gain and without internal gain. The photocurrent has a constant value, and you know that for photocurrent, IP equal to, the formula for photocurrent, IP equal to efficiency times E times with P, okay, the power, the incident power divided by HF. Okay, so we know that the diode delivers average electrical signal power to the load resistor. So the electrical power, you know that the formula for power is I squared R, right? So from P equal to I squared R, we can actually rewrite it as IP squared times with R. And you know that IP, the formula is this, and EP per HF, efficiency EP per HF. So this is actually IP squared times with RL. Okay, so that is the average electrical signal power. Okay, that's the formula. Okay, for average short noise power, average short noise power delivered to the load is given by I squared RL. P equal to I squared R. Okay, so from this formula, the short noise I squared for short noise times with RL. So it is actually the mean squared short noise. So this is the formula for mean squared short noise times with RL. So that's how you get the short noise power. And for thermal noise power delivered to the load is given by I squared RL. Okay, the thermal noise I squared times with RL. And we can rewrite it as 4 kT delta F. Okay, so that is thermal noise power. Okay, for the signal to noise ratio, it is actually the average signal power divided by average power of all noise. Okay, so this one is the average signal power, the electrical power, the average signal power divided by average thermal noise power plus average short noise power. Okay, so you just combine all the formula and you will get this formula. Okay, so usually IP, our photocurrent, is much larger than the dark current. Okay, IP much greater than ID. Then ID can be dropped. This situation occurs if the dark current is small and the optical power is not too low. Okay, so this is called as short noise limited or quantum limited. So the SNR can be simplified as this formula. Okay, so for this formula, for quantum limited or short noise limited, we will use this value of SNR. Okay, so this is the formula for the short noise quantum limited SNR. Okay, so by raising the optical power, it is effectively eliminated the dark current and the thermal noise. So the quantum limited SNR can be rewritten in terms of photocurrent as this formula. Okay, so the signal to noise ratio is equal to IP divided by 2E delta F. Okay, so this is the quantum limited SNR. It is more simpler. So it is easily modified the SNR equation to include photodetectors with internal gain. If the gain is M, IP increases by the M factor. The signal power P then increases by M squared. Short noise current is also amplified by the factor of M, its mean squared value, therefore it increases by M squared. The thermal noise current is not amplified because it does not depend or it is not generated inside the photodetector. Okay, so this is the modification that will occur if you have the multiplication factor. Okay, so this is the electrical signal power. Okay, so it is amplified by M squared. Same goes to the short noise. It is amplified by M squared, but for the thermal noise power, okay, it is not amplified because it does not depend on the photocurrent. Okay, so if the gain is large enough, the short noise far exceeds the thermal noise. By neglecting the dark current, so the signal to noise ratio will become like this. Okay, so if you can see here, the formula is the same as ideal quantum limited, okay, without internal gain. Okay, even though there is an internal gain, but the signal to noise ratio is still the same formula. Okay, used for the APD. Okay, if it is quantum limited. Okay, try to do this exercise. I also have already put the answer in the Google Classroom. Okay, so basically we have already learned on how to design an optical fiber communication system which consists of optical source, optical fiber, and also the optical detector. Okay, so just refresh back. If you have an optical source, it can be either an LED or laser diode. Okay, so these are the material for that sources and the operating wavelength. Okay, so we can have either gallium arsenide, indium gallium arsenide, and many other materials. And for fiber optical fiber, you can have either a single mode graded index or step index fiber. Okay, so these are some of the types of the fiber. Okay, so for PCS, you can have either a PCS. Okay, for example, it has attenuation of 10 dB per kilometer. For plastic fiber, it can be up to 500 dB per kilometer, the loss. Okay, and for glass, usually it is less than 1 dB per kilometer. Okay, and for the photo detector, you can have either PIN or APD because this is the most widely used as compared to PN. Okay, so that's why we just put PIN and APD. PN is not really being used now. Okay, so you can have either a silicon, germanium, or indium gallium arsenide photo detector. So with that, I end my lecture. Thank you everyone. Assalamualaikum warahmatullahi wabarakatuh.